Let's see. So given B in the flag array, so now just think. Generally, you can consider K of G mod B star intersect G mod K star. So if you want to think, so this is, if you want to put your other glasses on, this is intersect P. And said P is. That's the Cartan P that I would identify G mod K star with P and G mod B star with N. And I would look at the K orbit of N intersect P. And this is the closure of some K orbit on G mod K star, some nilpotent. So you get a map from KGB, a surjective map. Get a map from KGB to K orbits on G mod K star. G mod K star. So you would, the idea to parameterize the image would be to select some canonical representatives in KGB. And for SL2R, you don't have to select anything. These are, and for SL2C, these are just bijections. So these are bijections for, this is a bijection. In general, but in general, try to parameterize image by selecting representatives of each fiber. In some intelligent way.
Excuse me.
Yeah.
Is it always subjective? It's not really.
I think so, but let me think why that's true. I don't know why I'm spacing it out on that, but I do believe it's subjective.
It is. I forget too, but I remember that it is subjective.
Yeah, so there's probably some good reason actually why it's subjective, but I'm just spacing it, right? So, so this would be, and so this works perfectly for these guys. In general, it's not going to be a bijection. It'll be surjective, but not injective. And so the idea to parameterize this this interesting set of orbits, which is the sort of parameter set for these invariants that we've been talking about, is to select elements in the fibers. Okay.
It's worse. I mean, well, if you're talking about integral infinitesimal character, these associated varieties are special, and so there are a whole lot of nilpotent orbits you don't want, even though they do show up in this image.
Yeah. So so I'm just I was probably going to say something about special ones. I haven't said. Okay, so David brings up a good point. So maybe this is too ambitious because you don't really, maybe not. So this is surjective, we sort of agreed upon, but perhaps, and it turns out that not every nilpotent K orbit appears in the associated variety construction, at least when you fix integral infinitesimal character. So a refinement of this idea would be you don't need to do what I've said in parentheses, you only need to do what I've said in parentheses for a somewhat mysterious subset of things that are actually appearing for applications to associated varieties. So there's sort of a refinement of this idea which you might think would help you, that you don't have to parameterize every orbit in this way, but in fact that refinement introduces some additional complications which are hard to manage in a different way. Something like that. Is that what you were getting at, maybe?
Probably.
So this idea probably is hopeless, I think, except it works perfectly in the setting that Jonathan will talk about. So if and a few other settings, but so if O is an even nilpotent orbit, so what does that mean? So I should explain what even means. So O is okay. So I'll start doing something I resisted doing until now. So I'll identify G star with G, and I'm thinking of this orbit of a nilpotent element in G. Okay? So what does even mean? Well, and maybe I'll change the notation. I'll say it's an element E. So there exists a triple E, F, and H, and this is satisfying the SL2 relations. And the even, so this is Jacobson-Morozov. And even means that the eigenvalues of add H are even, and they can only be 0 and 2 in this case. So if I start with an even nilpotent orbit, so let me complete the sentence. This was supposed to be a pop-up window when you click on even or something. So in this case, then, this idea, this can be done very cleanly, very elegantly. Then so what I mean by this is this trie can be done very elegantly to parameterize OKI that appear in the associated variety construction for this this fixed even orbit. Okay? So in general, the idea is too ambitious. It's not maybe even the right one, but and the people who did this was done in ABB, and they figured out how to make this idea work perfectly. And so this is so Jonathan will do more about this. Okay, so we'll come back to that. So you've got these beautiful invariants. They're simple to define. They capture some serious information about the representation that we've been studying. How to use Atlas to get at them is a little bit interesting because parameterizing what they're made out of is interesting. We'll hear more from Roger about how to use the W, presumably the W structure of cells, because these things are constant on cells, the W structure of cells, or the coherent continuation representation in general, which we know happens beautifully, to compute some of these invariants. Okay, so let's see. Any questions about any of that stuff? Is there anything I should say, Jonathan or Roger, that you would like me to say? Make your lives easier? Okay, so since David brought it up, let me say it. So there's so this is a closing comment on this, that if X has integral infinitesimal character, so this is due to Bauer-Bogen, then the kinds of the nilpotent orbits that are appearing, complex nilpotent orbits, and the K orbits that are Lagrangian in them, are special. The complex orbits are some special. So not all complex nilpotent orbits appear in this construction. And I guess probably it's, I don't know why, I don't know, actually I don't know. But I think you can arrange every special orbit to arise in this construction. So this gives a characterization of special orbits. So
Special is a technical.
yeah. So special, yeah, so special has some meaning from the work of Lustig, previous, and so it means something technical, and it's, you could take this as a definition, so I should say all special appear in this way. So if you didn't know the definition of special before, you could take this as a definition. If you knew another technical definition of special, then this would connect these invariants with this other definition that you knew. So, and I should say that all even orbits are special. So this setting that I said, this idea works perfectly for parameterizing these K-forms of an even orbit is useful because it's for orbits that appear in this construction. Okay, but now, so a little bit, okay, so now I'm just kind of improvising here, but so a little bit more on special. So the Springer correspondence gives you a representation of W attached to any complex nilpotent orbit. To any complex nilpotent O, and I won't use all of the Springer correspondence. I'll just use part of it corresponding to the trivial local system. So one thing you can do with a complex orbit is take the trivial local system on it, apply the Springer correspondence, and get a representation, maybe I'll call pi of O, of the Weil group corresponding to this nilpotent orbit. O is special. You call pi of O special. Okay, so let's take a cell of Harish-Chandra modules whose associated variety of its annihilator is given by a fixed special orbit. And let's see if we can see that special orbit using the Weyl group. Okay, so here's a theorem. So fix a cell C of irreducible. I think it was either. So we're kind of. I've been thinking of these cells in two ways: irreducible Harshon modules or cells of parameters. But fix a cell of irreducible GK modules. With fixed complex associated variety O bar for O special. That's in the bilateral theorem. Now we have a W representation afforded by the cell. And we have a special representation, I should say that this is irreducible. It's an irreducible representation. I've got an irreducible special representation of the Weyl group. So I could see if these two are related in any way. And in fact, the special representation corresponding to the special nilpotent orbit coming from the associated variety appears, and I guess don't know the status of this, but it appears with multiplicity 1, partly an empirical observation made from exceptional cases. So this ties together the W module structure in the cell with the geometric invariance that we're getting from the associated variety.
Is that map of vector spaces or just vector spaces?
Oh, sorry. I put C. I meant to put that. Sorry. Thank you. So is that kind of clear? Because that kind of connects things nicely. So, okay, so this gives an interesting way to compute complex associated varieties, right? So how would you use Atlas to compute complex associated varieties?
You use a complex associated varieties command.
Is there?
No.
Okay. Okay, so this is great. So
Maybe it's worth saying explicitly that if you put a different special representation.
Yeah. So let me do it this way.
You could just put pi of O prime.
Yes, exactly. So this is 1 if the special representation. So this is supposed to be a special orbit. Yeah, I needed to say that. Thank you. So if the what I had written before is that if the special representation that you plug in to this, you look at the occurrence of a special representation in the cell. What I had written before is that if you start with the special orbit coming from the complex associated variety, you take that special representation, that occurs in multiplicity 1. So I should say, here. But what David was saying is that if you take any other special representation and plug it in, you don't get it. You get 0. So in the cell of Harish-Chandra modules, there's a unique special representation occurs in multiplicity 1. And that special representation is coming from, that special Weyl group representation is coming from the complex associated variety. Therefore, at least in principle, this means that knowing the W module structure of the cell representation, which is what Jeff explained, Atlas knows how to do. That's what he's kicked off with. plus the Springer correspondence. Allows one to compute associated varieties of annihilators of X. So the complex associated variety, the way you would compute it, is go into the cell, see what the W representation is. That requires already computing the cell requires the Cauchy-linguistic voting calculation. So that's running behind the scenes. So something difficult is going on, and something difficult is going to, and highly non-trivial is going to this calculation. Look at that W module structure, the way Jeff explained. Find the unique special representation somehow, in some way. Look up what complex nilpotent orbit that corresponds to in the Springer correspondence, and then you've computed the associated variety of ions. Okay? So that's pretty nifty. But the... Huh?
Did you write that down? What you just said?
Okay. Okay, so... Okay, so more explicitly, given X, some irreducible or GK module with, maybe it's okay if infinitesimal character row, okay, trivial infinitesimal character. Compute Z of C of X, the cell containing X, as a W module, as a W representation. Does that make sense? So go off, compute the cell that contains X, and see how, say, the simple reflections generating W, what the matrices for those are with respect to the basis of irreducible. And then maybe feed that to gap or something and decompose it in some way. So identify a unique, special representation pi appearing in Z of C of X. Okay. And then write pi is pi of O for some special, and again, secretly I'm always putting the trivial local system in the Springer system, in the Springer correspondence, for some special O using known tabulation of Springer correspondence. Okay. And then finally conclude the associated variety of the annihilator of X is O bar. Does that make sense? Now, a new set of ideas has to be brought to bear to compute the more refined associated variety. That David has many serious ideas about, and Jeff is implementing. And Jeff and David have many serious ideas about, both of them are implementing. And that I'm not going to talk about. That's where I'm going to leave the computation of associated varieties kind of hanging. But I think it's a very interesting, beautiful subject. And it's different than, well, the ideas are different than anything I've said so far.
So what about the other irreducible components there in cell?
Okay, so what about the full W module? The question is, what is about the full W module structure of a cell? It's very interesting. I mean, pretty much, I don't know, in many cases for the classical groups, you would recognize the cell representation of Harshchandra modules as a particular kind of left cell as a vowel group representation. It's maybe isomorphic to a left cell in the vowel group. That more or less probably is an accident in many cases. So it's hard to, I think it's hard to characterize what the vowel group representation on a cell of Harshchandra modules is. The only thing you can say is that the special representation occurs, even saying it occurs with multiplicity 1 is, I don't know, I mean, just that is maybe the most uniform thing you can say. Yeah, so there's a count you can perform. Okay, so let's do an example. So maybe this will be helpful. I don't know if you can think of these examples, but we can do an example. So let's take a look at GR as SP4R. SL2 is a little bit too simple to see anything interesting. So we have to really go up to something like this. Okay, so what's KGB look like? We can pull this up on the computer, but it's been done enough that we probably don't have to do that. Now, so the size of, oh, did I add another row? I combined G2 with SP4, isn't it? Okay, that looks better. Yeah, so 6, 10, 11. Now, the block of the trivial, yeah, so block of, I forget if you have to, I forget if you have to put that in there, but the number of elements in there is 12. Okay, so you're familiar with the D modules, things like this. So every one of these orbits supports a unique irreducible D module, and the open orbit has 2 on there. So the extra one, there's an extra non-trivial local system on the open orbit, which is contributing to this extra representation. Okay? So there's really, so the block picture would look like this, but at the top, so at the top there would be 2 representations. So I think it would look like this. Probably something like this. So this is the block of the trivial. So those are your 12 representations. So how do they break up into cells? So here's one cell, which has to be symmetric. Oops, I've drawn the wrong. Actually, it's interesting to draw blobs on this diagram too, but I want the different blobs. So let me draw the cells first.
No,
Oh, sorry, this one has 3. So the trivial is up here, a cell into itself.
That's too many, there were 5 cells. Okay.
0 to 5, I hope. I'm pretty sure there's 6 cells. So these are these, and so there's the trivial representation as a Weil group representation. So the trivial.
I'm sorry, what's the difference between this one on the right and the other?
So this is KGB, and what I've drawn is an order we really haven't discussed, but on the block there are 12 elements, and there's also an order on those. And I've drawn the order there, and it's very similar to the order here, except there's 2 on the open order. Okay. Okay, so maybe I should call this gamma trivial. This is our trivial parameter, if you want to think of the block consisting of parameters. And here's a holomorphic discrete series. And here's the anti-holomorphic discrete series. These are large discrete series. I don't know how to, the pluses and minuses are just arbitrary. And so what are some things? The Weil group representation on the block of the trivial, which is C, gamma trivial, well, that's the sign representation once again. And that's how you normalize the Springer correspondence. I'll call that the 0 orbit here. That's what it has to be, I think, for this to make sense what I said up there. So the sign representation is what the Springer correspondence attaches to the 0 nilpotent orbit. The cell is irreducible, that occurs with multiplicity 1, blah, 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 blah. Okay, so at the other end, you have these 2 element cells, and I could take one of the large discrete series, and that's going to be isomorphic to the trivial. Each of them is isomorphic to the trivial representation, which is pi of the principal orbit. So we better now draw the picture of complex nilpotent orbits for SP4R, because I'm getting beyond the ones that are totally uniform, 0 in principle. Okay? So